Okay, so now we are going to start the winner presentation session. I'm Bo Hyung-han at Seoul National University, and Torsen Settler will co-chair this session with me. We have three speakers. Each speaker will give 10-minute presentation, maybe 8-minute talk plus 2-minute Q&A. The first speaker is the winner of the challenge, Seung-gi Jung. The team name is Guitar. Congratulations, and let's welcome the speaker. Please start the presentation.
Hi. Um, Hi, my name is Seung-gi Jung. I'd like to demonstrate the first place solution to Google Landmark Retrieval 2020. Basically, as you can see in the figure, I used efficient net and global average pooling to extract features from images, and a deep neural network was followed to squeeze the features into smaller dimensions for compact representation and reducing model size. After that, cosine softmax was used to classify a number of classes. I used two trained datasets for this competition. One is Google Landmark dataset V2 total trained sets, and the other is the cleaned version of it. I simply call them GLD2 total and GLD2 clean. Now I'm going to describe basic configurations. For cosine softmax parameters, scale value was automatically determined by Aracos. Margin value was set to 0 because trained dataset is noisy, so I thought trying to cluster more between same class samples could make training more hard. I used weighted cross entropy to deal with imbalanced class distributions, and which were set proportional to 1 divided by log class count. Only left-right flip was used for augmentation because trained datasets are so huge that it was hard to overfit trained sets. Also, another intention was not to disturb the image distributions of trained sets because I can't use test time augmentation due to submission time limits. For the validation set, one sample per class which has more than 4 samples in GLD2 clean dataset was used. As a result, 72,322 samples were used for validation. The intention was to have as many classes as possible in the validation set while giving them the same importance. It is quite small size compared to large training data size, but validation loss correlated well with the leaderboard score. Now I'm going to describe training strategy. In the first step, GLD2 clean was used to train the model to classify 313 landmark classes. After validation loss converged, it scored 0.302 in private leaderboard for a single efficient net7 backbone-based model. Next, I took efficient net backbone from step 1 and used GLD2 total dataset to classify 203,094 classes. It scored 0.337, which was a huge improvement over step 1. From here, it was found that even though GLD2 total is noisy, it helps to make image feature embeddings to be more representative. Given that training on GLD2 total was successful, I tried to train the model from scratch using GLD2 total for a long time, but validation loss slowly decreased and the leaderboard score was much lower. This experiment showed that GLD2 clean is actually cleaner than GLD2 total, and it helps the model to learn important CNN filters. Third, the whole model from step 2 was used as is and was given increasingly bigger images. Since only input size has changed and the whole model was reused, training was able to converge quite fast. And some data augmentation effect was also expected, because different image sizes could give CNN filters a new challenge to optimize. For the result, it was found that bigger the images, better the scores. This step scored 0.353 for 640 size inputs and 0.363 for 736 size inputs. First, the whole model from step 3 was taken and loss weights for GLD2 clean samples were set twice. It was derived from the experience on step 2 that training too long with GLD2 total dataset could worsen the model performance. By changing the loss weight, I wanted the model to focus more on classifying GLD2 clean samples. The results showed that this step was effective. Finally, ensemble was used to increase the model performance further. Specifically, EfficientNet 7655 backbone-based models, which went through step 3, were used, and their feature embeddings were weight concatenated to make final feature embeddings. Embedding size for each model is 512, so in total 2048 size embedding was used. Weight was determined by the performance of each model, and exact value was chosen by inspecting a few submission results and choosing the best one. Finally, it scored 0.383, which is a huge improvement from before. Additionally, I made EfficientNet 7 backbone model to go through step 4, and it scored 0.386, which is the best score I've got. This is the end of my talk. Thank you.
All right. Is there any questions from audience? Well, currently we don't have any question. So
I can start by warming up by asking one question. So first of all, congratulations again, and it's very impressive to see the improvements you made here with very interesting techniques. So I think one of the aspects is that you use the full GLDV2, which we're glad to see that was helpful. In previous work, many people claimed that only the clean was helpful. So you show that, if used properly, using the full GLDV2 for training can actually give a substantial boost. So that was nice to see. I have two questions more specifically. One was about if you ever tried to use gem pooling, which was a technique that many teams in the Kaggle platform reported to use, and if that worked with EfficientNet or not.
I was using gem pooling at initial stage, and it worked poorly than GAP pooling, so I just dropped the gem pooling.
Got it. The other question I had was about the weighted concat. So if I understand, these are embeddings from the very same model, right?
Pardon?
So the weighted concat, I'm a little confused. I don't know if you mean that you have four different EfficientNet models, or if it is one EfficientNet model that you take intermediate feature maps and concatenate them.
It's all different models.
Okay, got it.
Yeah.
Any other questions?
I have a question too. Hello.
Okay, go ahead.
Congratulations from my side too. So you're saying that step 1 is really required so that the training in step 2 on the total GLD2 will work, right? So I'm wondering if the same holds for the training on larger resolution images. So did you try? Do you know like what happens if you try right from the beginning to train with larger resolution, or starting with smaller resolution is again required?
Actually, I didn't experiment with starting with large image input, so I can say which is better.
Oh, okay, so you're saying like, okay, you don't have any evidence, any like idea at the moment. Okay, and how about setting the weights of your concatenation? Did you have some systematic way to set these weights for the ensemble?
Sorry, I didn't understand.
You have the weight concatenation, and we can see in the slide the weights you're using per network. So how did you set these weights?
Weight was determined by the performance of each model, and exact value was chosen by inspecting a few submission results and choosing the best one.
Okay, thank you.
Thank you.
Right. I think the time's up. So we have to move on to the next speaker. So Torsen will introduce the second speaker.
Yes. So next up, we have the second place entry of the challenge, which is by the team by Min Yang, Cheng Hui, Xu Tongxu, Hui Ren, and Kai Wei. And the talk will be given by Hu Ren and Xu Tongxu. Please start. Andre, or one of the co-hosts, I think you need to give the presenters rights. Okay, perfect.
Hello. Hello, everyone. Our team is PYSJ, which comes from Baidu. We're honored to share the solution of the lemma retrieval competition 2020 with you. First of all, let's take a look at the task that the competition solved. As the owner said, we need to submit a TensorFlow 2.2 model to calculate MAP indicators. What is different from the previous years is that we can only submit.
I think we cannot hear you clearly. Can you speak louder?
Yes, I can speak louder.
That's great. Thank you.
Okay. We can only submit models without post-processing, including spatial verification, query expansion, and database augmentation. Second, all models must be run within 9 hours, which limits the number of models in Model Fusion. The official training dataset is GLDV1, GLDV2, and GLDV2 clean dataset. And there are great variants within the category of this dataset, which bring great difficulty to solve this problem. Our solution uses GLDV1 and GLDV2 clean dataset. Our solution is as follows. The picture shows the process of the entire retrieval pipeline. We choose ResToNet 200VD and ResNest 269 as backbone, adding embedding layer to reduce dimension to 512. Among them, ResToNet 200VD is used petal-petal chaining, and ResNest 269 is chained with PyTouch. As the picture shows, we use Archimedean loss as chaining loss to chain and Python models. First, we use same margin to train both models, use GLDV1 and V2 clean dataset and 224 resolution. Second, to maintain the diversity of training strategies, two models are used different training strategies. There's next 269 fixed learning rate on 0.001 and train with GLDV2 clean dataset, which resolution is 448. Then it is added gene pooling at last. ResToNet 200VD models was trained with increasing margin, increasing resolution, which is 0.15, 0.25, 0.35, and 224, 448, 640. This is mainly used to reduce the amount of calculation and accelerate the model convergence. In case the single model performance similarity, but the result of the ensemble is more competitive. To further expand the model difference, we fix the rest to net 200 VD conf layer parents and freeze the FC layer to chain with pre-processing in the test. In the final result, rest nest 269 with 448 resolution is 0.3697 in public and 0.3301 in private. Rest to net 200 VD with 448 resolution is 0.36507 in public and 0.32420 in private. The combine of the two models result of is 0.40176 in public and 0.36278 in private. Look at the pictures. We use margin to chain result with different margin. The single margin on similarity, the result of ensemble is more competitive. For resolution, increasing resolution chaining and infer helps improve the model effect. Table from 224 to 448, MAP indicators increased by 1.5%. From 448 to 640, MAP indicators increased by nearly 2%. In fact, it would be better if you can change a large resolution model from scratch, but it's too slow. And because the TensorFlow model will eventually be submitted, the model from PyTouch and PyTouch should transfer to ONX. Then use the ONX to TF code to convert to TensorFlow 2.2. All conversion code libraries is posted in the PowerPoint. Now conclusion, the main tricks we use. Large image resolution can improve model effect from 224 to 448 to 640. Adjust the main value will increase model diversity. Fix the solution parents fine-tune layer will be slightly improved by 0.2%. There is also some useless cheats. First, the smooth AP loss. We use smooth AP loss, which is present in ECCV forum, but we cannot improve MAP in GLDV2. And next, we can triple pair softmax. And it is also less than the margin loss. Third, we change some chip. Delete the black and white image, but less than the baseline. Finally, we have some doubles. It takes 6 hours by our converted nest 224 resolution. It was planned out by converted efficient P7 224 resolution. Some operations in the converted model may not have accelerated strategies in TensorFlow 2.2. We train TensorFlow 2.2 efficient P7, and it is inferred by 3 hours. So if we attend recognition condition, we will train the universal carriers models instead of PyTorch. Okay, this is the end of my talk.
Thank you very much. Are there any questions from the audience or the organizers? If yes, from the audience, please write in the Q&A box. And I don't know, are there any questions from the organizers?
I can start with one question. So I thought it was interesting that you use the arc phase margin decreasing over time during training. I wonder how important you saw this was for training the embedding, and how do you choose this kind of arc phase margin schedule? Yeah.
Okay, arc phase margin, if we choose 30 and 0.15, we can get normal result. But if we choose 0.35, we can improve the MAP by 1.1%. But the margin in different data sets is different. We change margin last year. The margin and still is 0.3 and 8. But it can use NAS to search the carrier instead of the name.
Okay, thanks. Are there any other questions?
I had a very quick question. So what's the reason of using multiple deep learning framework in your model training? Does it help the performance or for other reasons?
Pardon? I can't hear clearly.
What I mean is, what's the reason of using different deep learning network framework like PyTorch and Paddle in model training and convert it to the TensorFlow? Is that affect the performance?
No, we just have two GitHub models codes. We trained it by ours normally. TensorFlow are used best.
I see. Thank you.
Okay, thank you very much again. And we come to the last presentation of this session, which is by the 5th ranked team in the challenge. The members of the team are Nyen Tan Yan and Ahmed Erdem, and Nyen Tan Nan will give the talk. Please take it away.
Hello everyone. So my name is Nhân Nguyen, and today I'm going to present our team solution to the landmark retrieval challenge. So firstly, on the data preprocessing part, so we decided to train only on the clean data set, and for validation, we randomly chose about 120,000 images from the index set that had the same classes with the clean train set, and we computed the global average precision metric on that to check on the model. We use for augmenting the data, we first resize the image shorter side to a random number in that interval, and then we random crop 512 by 512, and then apply rand augment and cut out. On the modeling choices, because we so like I try to convert it because I use PyTorch for training models. So I try to convert the efficient nets to TF 2.2, and I couldn't succeed. So that's why I just like stick with the ResNet and SE ResNet variants for my backbones. So there were two architectures. The first one was a CNN with chain pooling and crossfade head. And the second one was the Delphi model by the host team. So for the generalized mean pooling, I froze the P parameter and set it to 3. And I adapted a bottleneck structure. So like from chain pooling, I reduced the dimensionality to 512 by a linear and batch norm 1D layers before feeding that into the crossfade head in order to reduce the computation. All our models were trained in either 10 or 20 epochs with ADMW optimizer and a web-up cosine Newlin scheduler. So through experimentation, we found out that focal loss and label smoothing were actually better than just cross entropy loss. At the inference time, we extracted features from 4 different models at scale 1, concatenate them together into a 2048 dim vector, and it took us about 8 hours and 20 minutes to generate the final submission. That score 0.3664 for on the public leaderboard and 32A7A on the private leaderboard. Yeah, that's all from my talk.
Thank you very much. Are there any questions from the audience or the organizers?
Could you clarify something? So you mentioned using cross-phase loss, but then there is a comment that you have like about cross entropy loss and label smoothing. So can you please like give some more details about this? What's the role of label smoothing and what kind of label smoothing do you use?
So like you know that the crossfade it's just like you added a matching penalty on the raw logics. So the focal loss I use a version without the alpha parameter. So basically you just like modulated the loss with gamma parameter. For label smoothing, I set the smoothing factor equal to 0.5. So 0.5 for the graduate class and 0.5 divided by the number of the remaining classes. And I think like either focal loss or label smoothing gave me about 0.2 or 0.3% improvement compared to just using cross entropy loss.
Okay, thank you.
Are there any other questions? This is also a reminder to the attendees that if they have questions, they can use the Q&A box to post them, and then we will relay them to the speaker.
While we may wait for the attendees, I have one other question. I see you mentioned that you extract the features for inference time at scale 1 for each model.
Yes.
Did you ever try doing multi-scale using pyramids and things like that, and if it helped or not?
Yes. So I actually try running inference at three different scales. So let's say for this model here, the SE ResNet 101 Delphi, I think multi-scale gave me 0.339 on the public leaderboard, which was not a lot. And also like it took like a lot of time to run models like inference at 3 different scales. So in the end, I just decided to do it at scale 1 only and ensemble multiple backbones.
Got it. Thanks. It sounds like it's advantage to actually ensemble different models instead of ensemble, you know, computing different scales. It sounds like.
Yes, correct.
Torsten, I think there's a question in the chat actually. I don't know if you saw that.
Yes. So the question is, the index set is around 8W. I wonder how to sample 12W images from this set, or 80,000 K, I guess, 80,000 and 120,000 K.
Yeah. So I think my local validation set had about 40,000 classes. So I just like, because I downloaded the index dataset and then I just like I kept the images that have the same class with the clean train dataset. So it's easier for me to like run validation for every epoch.
Okay, thanks. I don't see any more questions. And I think we're running out of time as well. So, Andre, back to you.
Yeah, exactly. Thanks, Torsten and William, for organizing this session. Thank you, everyone.